Now let us talk about one of the fundamental equation used in quantum mechanics, that is the Schrodinger's equation. So here we are talking about Schrodinger's time independent one-dimensional wave equation. Here we have two types of equations based on the potential field used. If the potential field is time dependent, then the equation will be called Schrodinger's time dependent equation. And if the potential field is time independent of time, then the equation is called as Schrodinger's time independent equation. Here in this section we will take Schrodinger's time independent equation. We will also take the simple case of one dimensional, that means the particle is moving in only one direction, say x-axis. So for this, let us consider a particle moving along x-axis with mass m, and it is associated with matter wave of wavelength lambda and frequency nu. So then we can have the wave function for this moving particle as a complex function given by psi is equal to a e power of I into kx minus omega t. Here k is the wave number given by 2 pi by lambda, and omega is the angular frequency 2 pi nu. Now let us differentiate this wave function psi partially with respect to x. So here the wave function psi is actually a function of the two parameters x and t. So we have to do partial differentiation, means we have to consider only x as the variable and time we have to consider as constant. So by that way, if we differentiate, we get the first derivative dou psi by dou x is equal to aik into e power of I into kx minus omega t. Now let us differentiate this partially once again with respect to x. Then we get the second derivative dou square psi by dou x square, that is equal to ai square k square into e power of I into kx minus omega t. Here I we know is the imaginary number given by square root of minus 1. So therefore I square is equal to minus 1. So if you substitute that, and also consider here a e power of I into kx minus omega t is same as the wave function psi. So then this becomes equal to minus k square psi, and k is the wave number given by 2 pi by lambda. So substituting that, we get minus 4 pi square by lambda square into psi. Rewriting this equation for 1 by lambda square, you get this 1 by lambda square is equal to minus 1 by 4 pi square psi into dou square psi by dou x square. Let us call this equation 1. Now let us consider for the moving particle the energy term. So let us assume here that the particle is moving with a velocity which is very small compared to the velocity of light. So in that case we will be talking about the non-relativistic case. In the non-relativistic case, the total energy is given by the sum of the kinetic energy and potential energy. The kinetic energy is given by the momentum term as p square by 2m, and potential energy is given by the potential field V, which we have considered here to be time independent. So therefore the total energy is given by E is equal to p square by 2m plus V. Rewriting this equation like this, p square is equal to 2m into E minus V. And now let us substitute for the momentum of the particle using the de Broglie's equation, which is p is equal to h by lambda, where lambda is the de Broglie wavelength of the matter waves. So therefore we can write p square is equal to h square by lambda square is equal to 2m into E minus V. Now we can substitute here for 1 by lambda square from equation 1. So if we substitute that, we get this minus h square by 4 pi square psi into dou square psi by dou x square on the left hand side is equal to 2m into E minus V. Rewriting this term, we get this dou square psi by dou x square is equal to, that is transfer this term over to right hand side, we get minus 8 pi square m by h square into E minus V into psi. bring this term to the left hand side, we get this dou square psi by dou x square plus 8 pi square m by h square into e minus v into psi is equal to 0. So this is the second order Schrodinger's time independent differential equation for one dimension, because we are considered only x axis. Suppose we consider a particle moving in general, that is for 3 dimension, then we can write it like this: dou square psi by dou x square plus dou square psi by dou y square plus dou square psi by dou z square plus 8 pi square m by h square into e minus v into psi is equal to 0. This is for 3-dimensional general case. Now this is the basic equation that is used in the quantum mechanics. Whenever we want to treat a given system according to quantum mechanics, we start with this Schrodinger's equation and apply this equation to a given system. And here we have to first substitute for the energy term, the energy and the potential energy term, we have to substitute in this differential equation and solve this differential equation using the mathematical methods. When we solve this Schrodinger's equation, we get the solution for the wave function psi. This solution will not be a single solution, it will be a n number of multiple solutions we will get. And also moreover, this solution will be very general solution with involving some arbitrary constants. Later on, what we have to do is see for some of the boundary conditions and initial conditions related to the given system, and when we incorporate these initial and boundary conditions into the system, we will be able to get from the general solution a more particular solution. Now this is also not final. We have to next go for the normalization of the particular wave function which we have got. Because we said earlier, normalization is one of the important steps in the quantum mechanics. Only when we normalize the wave function, we will be able to get the correct probability density values. So this is the method how the quantum mechanics runs using the Schrodinger's equation.